All right.
Sec. Perfect. So it started. Okay. Yeah. The floor.
Okay. I guess I'll start. So hi, I am Samuel Wauthier. I am a PhD student at UGent. I've been doing my PhD for a little over 2 years now. And I'm working on stuff like model reduction well, we work around active inference a lot. So model reduction within active inference. And well, I'm taking a little side road right now, looking into tensor networks actually. So yeah, that's me.
Okay, so
Welcome.
nice to meet you all. I'm Pietro, and I'm also a PhD at the University of Ghent. So the focus of my research is basically on unsupervised technique to learn objective for control or unsupervised representation. So there's a lot of model learning, exploration, but also reinforcement learning or kind of that. I do also do it in the key of active inference in the sense that I use it as the main starting point to then do my research. But I use it in a more broad sense, I would say. And okay, I think we can start with the presentation.
Yes. So let me see. Share this screen. Right. All right. So can you all see my screen?
Yes.
All right, thank you. So yeah, today we are presenting our paper from last year, May, I think it was, a learning gap between neuroscience and reinforcement learning. Yeah, so as you might know, there's a long history of cross-fertilization between neuroscience and artificial intelligence. So yeah, for example, deep reinforcement learning has been inspired by reward prediction error signals, or well, neural circuits, and this has allowed RL agents to perform better than humans on certain tasks, like Atari games or Go. But despite this, the latest achievements can mainly be attributed to incremental updates to the RL algorithm and to scaling up training to huge amounts of data. So lately, progress in artificial intelligence has been largely driven by benchmark problems. So think, for example, of ImageNet in computer vision, or well, simply Atari, as I just mentioned, or OpenAI Gym in reinforcement learning. And these benchmarks, at least in reinforcement learning, typically focus on increasing the complexity of observations or actions and the difficulty of finding rewards. So think of sparsity. But this makes it so we can argue that many aspects that are of interest in neuroscience are less prominent, such as uncertainty and stochasticity, or memory aspects. So we propose that we should once again draw inspiration from neuroscience and build novel benchmarks which can account for this. And this could foster new algorithms and at the same time provide empirical evidence for neuroscientific theories. So in the rest of this talk, we will demonstrate an environment which state-of-the-art algorithms struggle with, and give some examples on how we might go about solving it. So in 2016, Friston et al. Introduced a relatively simple environment. They introduced a T-shaped maze, as you can see here, which contains an agent and a reward. So yeah, imagine a mouse or a rat looking for a piece of cheese. Now, the cheese in this environment can be in one of two locations. It can either be in the left branch or in the right branch of the T. And so to show this, we have put two mazes here next to each other, with the cheese each in a different branch. And so these two mazes represent two possible contexts, two possible configurations that the world can be in. So the world is ambiguous. There are two possible contexts. And at the beginning, the mouse doesn't know which context it is in. So the mouse wants the reward, but without a way to tell in which context it is. It can only guess which branch the cheese is in. And well, what makes it worse, when the mouse chooses a branch, it is trapped and it can't escape. So it better choose the correct branch, otherwise it can never get the reward. So luckily, the world contains a clue, and the mouse can figure out in which context it is by going to the clue. So here, the blue circle indicates a world where the cheese is in the left branch, and then the green circle indicates a world where the cheese is in the right branch. And so the authors also point out that the key to solving this type of environment is by using belief-based methods, as opposed to belief-free methods like dynamic programming. And so we took this T-maze idea and adapted it into a game-like environment, which we called the E-maze. And so an important thing to mention about the original formulation is that it's discrete in everything you can imagine. So there are 4 locations: the initial location, which is the center, the left branch and the right branch, and then the clue location. And well, the mouse gets 2 moves to obtain the reward. So what we did in the E-maze is we provide observations which are a top-down view of the maze. And so here on the left, this image is what we would give the image, give the agent. And here on the right, well, we just removed the black areas to show you actually what the maze looks like. So here the mouse is this little triangle. The cheese is a yellow circle. And so the black areas are areas that the mouse is not able to see due to limitations like field of view, or because the areas are hidden behind walls, so the red walls here. And yeah, this is also called a fog of war for those who like video game terminology. So yeah, the mouse starts out in the center, like in the original environment, and you see here on the left images. And it can then turn either left or right, or go forward. So in this sense, the action space is still discrete. And also, like in the original environment, once the mouse enters a branch, the door closes and the mouse is trapped in that branch and it can't escape. But well, like the clue, the mouse can first figure out where the cheese is by going up here and looking through the windows. So this is indicated by the blue walls, actually. So these are windows and the mouse can look through them. So the mouse is no longer restricted to discrete locations, but it can move to intermediate points, like in an Atari game, basically. So yeah, that's the environment. If you'd like to play around with the environment yourself, you can also visit the link here at the bottom, and then you will have access to it and you can try it out. So yeah, I will now give the word to Pietro.
Okay, thanks, Samuel. I think I'll also need to ask you if you can switch the slides for me time by time. So let's start introducing the environment for a more theoretical point of view. So the environment can be described as a partially observable Markov decision process, where we indeed observe the environment through observation, but we don't really get the state of the environment. So for instance, by just observing the image on the left, the mouse has no clue about where the cheese is, and it's part of the state, whether the cheese is on the left or on the right branch. So this is one thing that makes it partially observable. The second thing that makes it a partially observable environment is the fact that indeed it needs to remember the information about the environment. So at every time step, you cannot get all the information about the environment. So it's not just its position in the environment, but also the time. Because for instance, if you saw the cheese, but then it turns in the other direction, unless he has some form of memory, he cannot remember where the cheese is. So he has to model it in some form of internal state. So if you can go to the next slide. So the baseline, we benchmark against this environmental reinforcement learning baseline. I think most of the people will know how reinforcement learning work, but I'll go through it very quickly. So the main idea behind reinforcement learning is that there is an agent that interacts with the environment through actions, and then the environment, in response to the agent's action, provides observation and rewards. And the key part of this interaction is the reward, because the positive reward should encourage desired behavior, while negative rewards are penalizing. So can we go to the next slide? So the objective of the agent in reinforcement learning is maximizing this function here. This is an expression of the expected reward that will obtain over a potentially infinite horizon by applying a certain policy. So the policy is represented with the p value, and we have this reward function r, which provides indeed a reward for every state and action. So if you are in a certain state of the environment, you act as an agent with an action and you get certain reward, and you want to maximize the possible reward that you get over time. Sometimes this quantity is discounted. Here I just left it undiscounted because it's not useful for purpose of explanation, but most of the time you will also see like a gamma close to the air that scales the reward over time, so that you actually get a better estimate with respect to the future and avoid having potentially infinite reward. So in our task, the reward can be obtained in either two ways. So you either get a zero reward for every action that doesn't bring you to a white point, so when you don't get on top of the cheese, while for the state where the mouse is on top of the cheese, you get a +1 reward. These are the only two ways that the agent receives reward. So the agent can be, as introduced by Samuel, described as a sparse reward task. So indeed, the only way to get the sparse reward is get into the cheese. So if we can go further. So baselines that we evaluate, of course, we cannot evaluate against all possible reinforcement learning methods because there is a huge number of them. So we decide to look at different kinds of reinforcement learning approaches. In particular, here I decided to split them up into two kinds of approaches, where we have implicit policy reinforcement learning methods and policy learning. So what do I mean with implicit policy? I mean that the agent, instead of estimating for the state of the environment the action to take, it estimates for all possible action what's the value that they expect from that action. So at each time step, the implicit policy that he has is taking with a generally high probability, because there's also some kind of exploration. That's why it's called epsilon greedy, because with epsilon probability, you get a random action, but most of the time, the agent will just select the action that brings the highest value to this output from this estimation network. This is normally the Q learning methodology. So you have the Q network that estimates the value, and you follow the action that has the highest prediction from the Q network, and belongs to this category methods like DQN and Rainbow. In particular, I would say that Rainbow is basically several improvements that have been done on top of the original DQN work, which was the first deep reinforcement learning method applied to pixel spaces, or in the Atari, the original Nature publication. And then we have these policy learning methods. In the policy learning method, for each state of the environment, you actually try to infer directly the action. So you infer normally a probability distribution of an action, and you then sample from this probability distribution, and in that way you get an action. At this point, it's also important to highlight that in our environment, the action are discrete. So of course, otherwise you cannot apply implicit policy methods. We also have worked with a continuous action version of the environment, but in the final version that we released for the paper, it was discrete action. So if we can go to the next slide. So the other biggest split up in terms of reinforcement learning methods, I would say, is model-free and model-based methods. So model-free methods basically train on past experience to learn a policy in the environment or an implicit policy. So belongs to this category, methods like PPO, DQN, and Rainbow. And the difference with model-based algorithms is that the model-based algorithms train first a model on the experience from the past, and then use this model to plan and to learn the policy. So for instance, the way it is done in Dreamer is that you first train the model on the experience from the past, and then you use your model to roll out some potential trajectories that can actually happen in the environment and train a policy on these imagined trajectories. So you can proceed. So finally, the other important idea in reinforcement learning that we want to test is exploration. Because of course, in the environment, in the he-maze, it is important to explore in order to first find the cheese, or also equally find the hint that tells you where the cheese is. So we find a few strategies that we could have tried on the environment for exploration. The first one, we called it PPO with orthogonal init. So what is this? This is just a basic way that they use to provide a better implementation of PPO. So if you provide like a good orthogonal initialization of the weights of the value network, you basically get some form of optimistic estimate of the values at the beginning, so that the agent will first try out some action in order to explore the environment. So this actually helps at least getting some initial random behavior that is better explore the environment, is better distributed in the state space. So then we have ICM, intrinsic curiosity model, and this is a method that explores by providing an exploration bonus to the agent, which tells the agent to look for areas of the environment that the agent's model is not able to predict accurately. So whenever it's not able to predict, it will try to go there and see what's happening in there. And then finally, we have R&D, so random network distillation. This is another exploration bonus method. So we again provide an exploration bonus to the agent, and here the agent looks for unseen observation, in that it tries to just predict the observation and see if it's able to model it with its network. It has a network that basically tries to predict the distribution of the data projected into a random state space, and then see if this image was seen before or not, and looks for this area. So now I think we can discuss the results. Samuel, you can go ahead. You're muted, I think.
Sorry about that. Yeah, so we measured the performance of each of these algorithms on the environment in terms of return. And in this case, this basically measures how often the agent was able to reach the reward. Because in practice, the return is the episodic sum of rewards, which in our case is 0 or 1, since the reward for getting the cheese is 1. So we show the rolling average over 100 episodes, and this gives an estimate of how often the agent is able to reach the reward. And actually, the blue line here shows the average over 10 different runs. So yeah, and the shaded area shows then the range between the maximum and the minimum obtained in those runs. Now, with the stochastic nature of the environment, if an agent were to simply choose a branch randomly, it would reach the reward 50% of the time. So this would correspond to a return of 50%. And so we will say that an agent has to reach the reward more than 50% of the time to perform better than this random agent. And well, this is important because an RL agent is not guaranteed 50% performance when it is only allowed to make a limited number of moves. And this is because it may never learn to go towards the reward because it may never reach the reward if the environment is sparse and there's only a limited number of moves. So in fact, as you can see, the model-free methods, PPO, DQN, and Rainbow performed rather badly, with DQN and Rainbow actually failing to learn at all, and PPO reaching only about 10% of the 10% return. Adding exploration to PPO does improve the performance by quite a bit. And finally, Dreamer, the model-based method, was the most consistent in reaching 50%. But well, none of the methods ever performed better than this random agent that we said earlier. And so to give you an idea of the behavior of these agents, we have here an example from PPO. And on the left here, the environment has been adapted so that the branches don't close when the mouse enters them. And this is just to show the behavior of the PPO algorithm. So I don't know, can you see the video? Okay. So yeah, as you can see, the agent learned to go to the reward, but it developed the habit of going to the right branch first to check if the cheese is there. And if it isn't there, it will go to the left branch. So here you see it going to the left branch. And here again, going to the right branch, and the cheese is there. And so on. And then here on the right, we can show you how the agent behaves when the branches do close. So this is a different agent from the video on the left. This one was trained on the environment where the branches do close. And well, you'll notice that the behavior is kind of similar. So it will always go to the left branch. Sometimes it might get stuck for a bit, but it will always go and have a look, as we'll do in a second. And it will get the cheese. But so yeah, it goes to the left without checking if the cheese is actually there. And at a certain point, it will get stuck. And will get stuck there until the end of the episode. And so this is how it can never perform better than the random agent. Yes.
So what you showed here is you train these different actually the other slide with the baselines. You train them and they have a fixed number of steps, right, to reach the goal. Is that correct?
Yes. Yeah. So yeah, sorry, I didn't mention this. It has 250 steps to reach the end, and after that the episode is done. And it takes around 50 steps to go from the starting position up to to look through the windows and see where the cheese is, and then go to the cheese itself.
But then do you use the same principle also with the random policy?
No. So this is like an ideal case. That's why I mentioned this random agent that I mentioned is like an ideal case. If you have an infinite number of moves, basically, you will never do better than 50%.
Yes, with the but then if these reinforcement learning baselines didn't have a limit in steps, then they would perform probably better than the baseline.
Than the random agent, you mean?
Yeah.
Well, I don't think so, because I think they just randomly select a branch without looking where the cheese was before, and which is the same as just randomly choosing a branch, which would give you the cheese 50% of the time.
Right. Okay. Thanks.
No problem. So yeah, in the case of this PPO example, the agent never learns to have a look through the window before choosing a branch. And together with the fact that stuff like orthogonal initialization helps the agent perform a little better, this kind of demonstrates also how sensitive these algorithms are to choices of hyperparameters and clever tricks like orthogonal initialization and things like reward shaping. So I'm sure you could solve it if you did some reward shaping. But well, this just shows that the details often determine whether the algorithm will be able to solve a task or not. And there is no default setting which allows the algorithm to generalize well to any environment. And so how would we go about trying to solve this environment? Well, first, we would have to think of what are the potential problems. And one of those things is that, well, there is a large time frame between the moment the agent can see the reward through the windows and the moment the agent has chosen a branch and can see the cheese again from the other side. And well, this is a problem because the agent needs to remember where it saw the reward. So if you just imagine the shadows again, like once it's past this point here, it won't see the reward anymore, and it will have to remember where it was. So in the sense, model-based methods contain a type of implicit memory, in the sense that the model can contain a representation of where the reward is located. And of course, as we saw with Dreamer, this is not a guarantee that the method will work. Like an additional difficulty here is also that it has to form this representation based on the small amount of time that the agent actually gets to see the reward. So yeah, in the entire episode, there is probably only a few frames where it can actually see the cheese. But more explicit forms of memory would be LSTMs or GRUs or memory networks. But we might have to look towards methods which are grounded in neuroscience, such as Hopfield networks or maybe Canerva machines. So yeah, I will give the word again to Pietro.
Right, so we just discussed about having memory that helps with the partial observability of the setting, so remembering the dependencies between different observation in the state space. So let's now talk about the other big problem, this actually going to get the int. How do you get the int? So I believe, and it is also part of my research, that the best way to do exploration in that sense, that you should have a latent representation of the state space, so something that represents the state in the model, and then you perform some information gain computation with the observation that you get from the environment. So you could use that as an intrinsic reward in order to stimulate, foster exploration for the agent. So in the case of the maze, this means that you have a good latent representation of the state. So your model in the latent space is trying to model where the cheese is. And whenever you actually go and see the int, that part of the space is which was uncertain before, it actually becomes a narrow distribution. So you get a big information gain in that case, and that's what you want to do before actually going for the reward. So your model first acknowledge where the reward is situated, and then it goes after it. That I think is the strategy. I've also shown in one of my most recent work, which was curiously published in the same period at a workshop first at iClear, and then now it's going to be published AAAI, that if we use this kind of Bayesian surprise or latent Bayesian surprise, latent information gain, we do very well in exploration. I benchmarked my method against a lot of Atari baselines, DeepMind controls with baselines, and it worked very consistently. So it was interesting to see that indeed information gain is a very good metrics for exploration, and it also helps resolving ambiguity in the environment. If we go to the next slide. So here I just provide some hint of what is active inference, which is kind of the focus of our group. So active inference is another binary theory we can say it's about control, but it's generally about more than that, not just control, but self-organization of organism and more complex biological stuff, to say the least. So in general, this in active inference, we minimize unexpected free energy functional, which I would just show here and say that it can be split up in two terms. One is indeed the information gain that I showed you before, and the other is a preferences likelihood term, which can basically just be replaced by a reward term. So in active inference, what the agent does is indeed looking for these two kind of things, maximizing the information gain and maximizing rewards. In this case, we see they are negative because I say minimizing free energy, so maximizing information gain, maximizing rewards. And I think that is a key part in behavior in order to solve this task. So that you first indeed gather the information that you need, and then you apply a reinforcement learning like algorithm in order to get to the reward, because that's what reinforcement learning does most of the time, getting directly to the most rewarding states, to the most rewarding trajectories. So if we go to the final slide. So to wrap up what we presented, so we developed a gym environment inspired by neuroscientific experiments, in particular the maze designed by Friston et al. That we still see on the right. It was a very low dimensional and very simple environment. It was also partially observable, but it didn't look that difficult because it was just 4 states. So it could be solved probably with a simple model of the environment and a belief-based policy. So we made it more complex because we added high-dimensional observation, and we make it continuous in the state space. So the state space is actually infinite in terms of possible position of the mouse, or similar, nearly infinite. So we benchmarked several reinforcement learning baselines and found that there is indeed a learning gap in this problem. So the agent doesn't go for the information that it needs to get the reward, but it just tries to greedily get to the reward. And that is the learning gap we were hinting at the beginning. And we also showed some potential ways to approach the problem. In particular, we'll again highlight they are, in our opinion, memory. So to fight the partial observability problem, to get a memory that allows you to remember what's the state and where the cheese is in our case. And also exploration, because of course you need to go to get the hint. You need to have that information again in your model that allows you to know where the cheese is going to be, left or right. And then finally, we wanted to encourage with our work to tackle more problems inspired by neuroscience in general, because we believe that there are many interesting case of studies in neuroscience. In reinforcement learning, indeed, they focus a lot on making just the problem more complex to solve with the actual baselines, where indeed there are a lot of complex problems that are not explored, or maybe they're just not ready to be tested in silico with these approaches. And if we want to go towards a more intelligent artificial agents, that might be the case that we also look at them. And yeah, that's it. These are our contacts. And this is we also have a Twitter of the lab and a blog page. So we also normally post some blog posts on our blog if you want to check them out. And thank you for the attention.
So, do you have any questions?
So I thank you for the presentation. It's very nice. Did you compare with specialized? Did you test it on specialized partially observable MDP methods, like for example LR2, RL2, or the recent very bad, for example?
We didn't exactly test again RL2 and very bad, which I know they are basically meta reinforcement learning approaches. But we did test a recurrent PPO method, which should basically account for the partial observability. So we did test this baseline where we just added an LSTM to PPO, which is kind of also similar to what happens in RL2, but you just don't have the inter-episode recurrent neural network. So it was just an episodic LSTM. It might also be interesting to test with if removing the inter-episode constraint, then that might help and eventually solve the problem. But I struggle to see how it could understand how to get the int. I believe that it could actually learn different policy, because that's also what happens with these methods for multitask and method reinforcement learning. But I at the moment, but I may be wrong, I don't see how it could go towards the int to check where the cheese is.
So which, you talk about RL2?
Yes.
Well, so if it has memory, it can get a hint in theory, right? Then of course it could be that in practice it doesn't train it.
Yes, in theory, yes, but with the STM, just equipping a TPO in STM, that wasn't enough, probably because it was forgetting. I mean, LSTM can remember like, what, 10 steps, 20 steps. I don't think they can deal with a 50 time steps dependency. So maybe when we did this, transformer weren't that much top notch, but now they are. Maybe if we tested the transformer, that could already change things, but still has to figure out that you need to go to the end first and then memorize that for the long term.
Yeah, and I mean, again, for very bad, it's more plausible that it will work, because then it's actually storing a representation of the environment. Then of course it's still a practical matter whether it could still forget, but it's at least it's trained in order to not forget, which that will be quite interesting actually to see if you can make it work in that context.
Yes, I think it might be interesting. If I remember, Varibad also has this latent task representation, so you could basically split the possible environment into two and infer whether the cheese is on the left or on the right. So I don't remember if there is.
I don't think that Varibad is using a specific latent task label. I think it's just using, right, guys?
That's correct. Varibad just has some generic hidden state vector, like the thing in the autoencoder, which is of size 5 as an input. The state input is just coordinates, and the output is also coordinates.
So yeah, I think that the problem may still be, how do you infer if I'm on the left case or the right case? Is there an information gain? And if there is, then yeah, maybe it would help towards this kind of environment.
I mean, if the autoencoder works properly, so if it trains the autoencoder, then it should be able to solve it, because then the autoencoder keeps the memory, except that Varibad is designed that the memory could still drift. So while it's designed as an iterative inference, it doesn't constrain the fact that the information is maintained, which could mean that in practice it has a GRU, so it's still the fact that it could forget.
Yeah. Okay. Yeah. I get it. Okay. Yeah, might be. If you eventually solve it with a very bad on our environment, let us know. It will be also interesting for us.
So you have your environment. You just shared it, right? So if we want, we can just use it. Okay.
Yeah, that's right. If you want, I can show you the link again.
Yeah. It's I like the environment. I think it's very cool. What do you think, guys? Do you like the?
Here it is.
Yeah, I think it's indeed very cool. I feel like it's the simplest environment you can get that includes attention seeking and not attention information seeking behavior first, or it actually makes it necessary to seek information in order to optimally solve the environment. Like I don't think I could think of a simpler environment that would achieve the same sort of thing. Like I think this problem is neatly isolated in here, which makes it very nice for testing and comparing methods.
Yeah, indeed, and yeah, maybe we could decide also to use that in our work. So you said that this is inspired to neuroscience. So actually, can you point out to neuroscience papers that they use this environment in animals?
I haven't seen this environment in actual animals, just simulation actually. So, well, the one paper where we got this idea was actually an active inference paper. by well, Friston and some colleagues, and they just use this to demonstrate the ambiguity resolving nature of active inference, actually.
But you don't know actual neuroscience work using this protocol.
There is neuroscience work where in the long shaft of the T-maze, there is still information for the mouse in the form of sticks, either on the left or right side. And then the mouse has to essentially count on which side there are more sticks. And then that will be the side where the reward will be. So the mouse has to learn to count the sticks in order to get the clue where the reward will be. And this is a fairly now neuroscience experiment.
So wait, the mouse has to count how many?
Exactly. So in the slide you're seeing right now, you can imagine that on the left and right side of the mouse, there's some hints in the form of just some matchsticks or something like that. And the side that will have more of the sticks will be the side that the reward is on. So it's used for learning the cues. And if I remember correctly, one of the experiments that was done with that was that at some point after the mouse has successfully learned to count the sticks, they reversed the cues. So all of a sudden, they placed the reward, the cheese, on the side where there's less sticks. And then they wanted to see how quickly the mouse can switch. Obviously, it had learned that the amount of sticks had something to do with the position of the reward and how quickly they could get that it's now the other side where there's less sticks. And that is a neuroscience experiment that has been done multiple times in literature.
And what kind of region, what neural activity do they measure in this setting?
That's a good question. I'm going to look up a paper in the next few minutes and send it in the chat.
That would be nice.
If I can add, I believe that also Friston in one of his several papers cites some of these related experiments to these teammates. So probably if you look in some of his paper about the epistemics values or visual foraging, these kind of things, you may probably find some additional references to neuroscientific studies, these kind of problems.
Okay. Are there more questions or comments? Otherwise, I think, yeah, we can close the presentation. Thank you so much, both Pietro and Samuel. It was a very good presentation.
Thank you for listening.
If you find the paper, could you just send it to me, just or to Gianluigi?
Absolutely.
Like by email. Thank you. And that will, because I'm setting up a project with some neuroscientists, and yeah, that's relevant background.
Because and this I don't remember 100%. I will definitely look this up. So please take the second information now with a grain of salt. But I was under the impression that this particular problem that I just explained to you had already also been solved by reinforcement learning agents. But then I must admit that I'm not exactly sure on the details of if this was PPO or not, or in what form. It was likely fully observable because if I remember correctly, this was a few years back, and then a lot of stuff was focused on fully observable stuff.
Yeah. Okay. Thanks.
Okay.
All right.
Thank you very much for your presentation.
Thank you for coming. Bye-bye.
Thank you. Bye-bye.
Thank you for having
See
us.
you.
Bye.